Um, so today we're actually going to sort of move past differential equations just briefly, and we're going to talk briefly about what are known as integral equations. So an integral equation is an equation involving integrals just as a differential equation involves derivatives. So to get an idea of what we mean by that, let's just sort of look at some solutions. Or some examples, rather. So you could have something like, y of t is equal to the integral of y of t dt. And as you might be able to guess, this has general solution y equals c e to the t. Not very surprising. They could also get more specific though, so you could have y of t equals 3 plus the integral from 0 to t of 2 y of w dw. And this one, oops, has as its solution y equals 3 e to the 2t. Just another example just to see they can get a little bit more complicated. So I could have the integral of 0 to t of y, but instead of plugging in w, I plug in w squared. And that whole thing is equal to 1. Now, I don't actually know what the general solution of this is, or if it's even recognizable, but one solution is y equals 1 over t. So just to, double check, really just trying to emphasize, try to get you to understand what it means to be a solution of an integral equation. So if I plug in something like this, right, y equals c e to the t, or I think that one's clear. Let's look at this one. So in part because now that I look at it, that might need to be a 1/2. Let's check. So what's 3 plus 0 to t, the integral from 0 to t of 2 times 3 e to the 2t. Okay, well, to evaluate this integral, I can do a u sub. U is dt, du is 2 dt. Oh, and I am not being consistent. This should be w and dw. And I have that 2 dt there, so then I just end up with 3 e to the 2 times w. plug in a 2 and a 0 for w, and I get 3 plus 3 times e to the 2t minus 1. I can verify that, yep, at the end, after I do that cancellation, I get exactly what I started with. Similarly, down here, 1 over t plus the integral from 0 to t. Oh, wait, that shouldn't be 0, that should be 1. Yeah, that would be, otherwise this would diverge. 1 over w squared the integral of that is w to the negative first divided by negative 1. And then here I'm going to have minus 1 over t, and then minus, plugging in 1 gives me 1 over negative 1. So that stuff cancels, 1 over t minus 1 over t plus 1. And at the end, I get 1, which is what I wanted. Okay. So yeah, so this is what it means to be an integral equation. This is what it means to be a solution. So similarly, an Integro-Differential equation involves both integrals and derivatives. So, examples of stuff like this might be for y equals the integral from 0. Well, let's start with maybe something easier. How about just y prime equals the integral from 0 to t of y. Could also have something like y, or 4 times y of t, is equal to the integral from 0 to t of y of w prime, that whole thing squared, dw. And let's just verify that this is true for has y equals 4t as a solution. So if y is a 4t, right, then y prime of w is just 4. And so this whole thing, on this side I have 4 times 4t equals the integral from 0 to t of 16 dw and here I'm going to get 16t minus 0, and the other side is also 16t, so 16t equals 16t. Can confirm it verifies it. Lastly, to give one other example, let's look, we could have something like y prime of t equals t plus the integral from 0 to t of w squared times y of t minus w. And note here that I can rewrite this as the convolution of t squared and y of t. So this last example is sort of the stuff that's very similar to what we're going to be looking like. So in particular, there's a particular type of integral equation and these are called Volterra integral equations. And these are integral equations of the form so y of t equals f of t plus the integral from 0 to t of k for some function times t minus w times y of w dw. And note the reason sort of why you were studying these, this is just the convolution of k of t and y of t. Okay, so to learn how to solve these, let's just start with an example. All right, so we have our integral equation, and you might be able to identify this as y of t equals t plus the convolution of t and y. So of course, because we're learning about Laplace transforms, what we're going to do is just take the Laplace transform of both sides. Laplace transform of t is 1 over s squared. And remember, when we take the Laplace transform of a convolution, what we end up with is the product. So 1 over s squared times, well, whatever the Laplace transform of y is, capital Y. So I'll go through, multiply through by s squared, so I get s squared times capital Y equals 1 plus y of s. And so I get y of s equals 1 over s squared minus 1. Okay, so I need to do a partial fraction decomposition. This one is pretty straightforward. It's going to be 1/2 over s plus 1, sorry, s minus 1, minus 1/2 s plus 1. So from that, we can get our solution by taking the inverse Laplace transform and see that y is equal to 1/2 e to the t minus 1/2 e to the negative t. Okay, So like, let's look a little bit at the general case. So we have this, and we're just gonna, so in practice, right, you'll be given f and k. So f of s is going to be the Laplace transform of little f of t, and capital K of s is going to be the Laplace transform of little k of t. Right, so we know we can rewrite this like this. Taking the Laplace transform of both sides, we get capital Y of s equals capital F of s plus capital K of s times capital Y of s. We can move that over to the other side. And so we get, solving for capital Y, we get that. And so we can just conclude that y of t is the inverse Laplace transform of f of s over 1 minus k of s. So you're welcome to use this if you want, or you can just sort of go through the steps every time. So let's look at one more where there's a little bit of a trick to it. So the trick here is, it doesn't necessarily look like this is the Laplace transform, or rather a convolution of anything with y, but, right, we could add a 1 there, and then we get y minus the convolution of 1 with y equals sine of t. So now again, we'll take the Laplace transform of everything. Remember, the Laplace transform of 1 is not 1, but 1 over s, and then y minus s equals, Laplace transform of sine is 1 over s squared plus 1. Multiply through by s to get that, and then distribute and divide, we get this. All right. At this point, we would do a partial fraction decomposition. I'm not going to do that step. It's a pretty straightforward one. And now we take the inverse Laplace transform. So we get our final answer is, I can just pull out the 1/2 out front, e to the t minus cosine of t plus sine of t. All right, and just to close it out, I'm going to do one more example. This one's going to be an integro-differential equation. So there's a problem like this on your web work. So much like for second order differential equations, how you need an initial condition, the same thing sort of happens here. All right. So we'll rewrite this first as a convolution. And now we'll take the Laplace transform of everything. So here, remember, because we took this derivative, we're going to need this initial condition. So S times capital Y minus 3 minus convolution becomes a product. So S over S squared plus 1 times capital Y. And then the Laplace transform of t is 1 over S squared. So to help, I'm just going to multiply through both sides by S squared plus 1. Move this term over to the other side. And I'll also note that I can write this as a 1 plus 1 over S squared. Okay, if I can combine this into 1, I just get S cubed Y. And then over here, I get 1 plus 1 over S squared plus 3S squared plus 3, or 3S squared plus 1 over S squared plus 4. Dividing through by S cubed, I get Y equals 3 over S plus 1 over S to the 5th plus 4 over S cubed. And now I just take the inverse transform. All right, so I pulled out a 2 here so that I have 2 factorial over S cubed. And I want to do the same thing here. I'll multiply the top. I'll multiply by 4 factorial on the inside, and then divide by it on the outside. Now I have 3 plus, that becomes t to the 4th, so t to the 4th over 4 factorial, and then plus 2t squared. And that's my final answer. All right, we will end it there. This is also the last video for sort of this part 3 of the class.